Suppose you have a force field, not the science fiction invisible wall, but a field where you have a force at each point in space, the physics kind. Maybe you have a mass in a gravitational field, and for each kilogram of mass you're going to have a force in the direction of the field. Or maybe you have a charge in an electric field, and for each coulomb of charge it's going to experience a force in the direction of that electric field. Now those forces are going to cause those masses or charges to accelerate, which means they're going to change direction, move faster or slower. And if you want to track what something's doing, if you want to know how fast it's going, then you have to kind of follow it moving. You say, all right, it moved a little bit that way, and then the acceleration caused it to change, and then it moved that way, and then the force was in a different direction, and you got to follow all that. But in gravity, sometimes there was an easy way to do that, using energy. And that was because gravity is a little bit special. It's what's called a conservative force. And we can do exactly the same thing for the electric field. So we're going to try and motivate and explain the electric potential. So I said this had something to do with energy. Let's think back to gravity again. Suppose we have a roller coaster, and you start up here. Here's us, we're a sphere, and we're going to roll down this roller coaster, and we go down and up and down and up, and we ask the question, how fast are we going to be going here? That might be really important, because if we're going too fast, maybe we'll detach from the rails at this point, and we'll have a serious issue. And so we can work out the velocity there two ways. The first way, which is by far the worst, is we can say, well, I know what the force of gravity is. The force of gravity is always pulling me down. And I also know that there's a force produced by the roller coaster, by the wheels and the track, to make sure that I stay on the roller coaster. And so the roller coaster is going to provide whatever force I need, force roller coaster, so that I stay on that roller coaster. And so these two forces are going to add up to keep me on that roller coaster, and I can figure out what my acceleration is all the way down here and all the way up. And each little bit of time that I travel, I'm going to have to look at the new force created by the roller coaster to make sure I'm going. And the faster I'm going, maybe the stronger that's going to have to be. And it's going to have to go all the way around here. And I'm going to have different directions. I'm going to have to add up the force in the horizontal and vertical directions. I'm going to have to add all that up to figure out the velocity. Or I could cheat, and the cheating method is to say, let's assume that this roller coaster doesn't have much friction. And if it doesn't have much friction, then I'm going to have the same energy at this lower point as I did up high. And if I have the same energy, and I've only got two kinds of energy, I've got gravitational potential energy and kinetic energy. And so if I spot that the change in potential energy, which is just proportional to the height difference, is equal to the change in kinetic energy, then I know how much extra kinetic energy I have, and therefore I can figure out how fast I'm going. Now if we take out the complications of the roller coaster and just have, say, the gravity due to Earth, then we have a vector field all through space. So for each point in space, I've only drawn some of the arrows obviously, for each point in space I have a gravitational field which is directed towards the Earth, and if I put a mass there, it'll experience a force proportional to that mass. So if I want to calculate how some kind of satellite or comet is whizzing past the Earth like this, then again what I'm supposed to be doing is I'm looking at, say, this point here, and I have to look at the force at that point, and so I have to calculate exactly how that thing is going to accelerate. And so you can see that that force is going to accelerate this particle that's coming in by both making it faster and changing its direction slightly. And then when it moves a little bit over to here, I'm going to have to do it again. I'm going to have to look at the new, slightly different force vector and then calculate how that's going to change its velocity and repeat, rinse and repeat. And then as I do that, I'll get all the points of my curve as I go all the way past the Earth, hopefully past the Earth. We don't want our things slamming into Earth, that can be bad. But if I just want to work out, say, what the velocity is at this point here compared to this point here, then I can use an energy argument. Now how would I normally work out how the energy changes in an arbitrary force field? Now when a force is pushing on a particle and it changes its energy, that energy change is called the work. And when the particle is moving in a straight line and the force is constant, we know what to do. And so to approximate that, what we do is we take the curved path and we just zoom in on a small piece of it. And if we zoom in on a small enough piece, then that path is going to be straight and that force is going to be constant. And if we call the distance s, then the work done is just going to be s times the component of the force in its direction. And so the force we can break up into a component that's along the direction of that motion and at right angles to the direction of that motion. And this component here, the component along the direction, the work is just going to be F times S. So if this force was in the opposite direction to the motion, then we'd get a negative number, and indeed the work would be slowing you down. It'd be taking energy away rather than adding it. And if it's in the same direction as the motion, then we get positive work, we're adding to the energy. So if we want to find out how the energy of our particle going around the Earth is changing, then all we have to do is we have to break up our motion into small pieces like this and calculate the work. That still sounds hard. In fact, it hasn't really gained us much because we still have to break it up into pieces and add them all up, and that's the hard part, right? And we've still got all these different directions of the force vector and different directions of the motion, and we have to figure out the components. It's complicated. But there's another thing that makes it really simple, and that's because gravity is a simple special force called a conservative force.